Hello, everyone. Today, I would like to introduce our recent work, Remote Direct Memory Introspection. This is a joint work from Rice University, MIT, and Duke University. Security is the first-class objective in the cloud. The problem we are targeting today is a branch called memory introspection. Memory introspection is a critical security task. There are a lot of root-level compromises, such as rootkit attacks. Take this virtual file system attacks as an example. The attacker modifies the iterate pointers into its own malicious implementation so as to hide its traces from forensics. For such attacks, security applications relying on the operating system won't work, as they will be tricked by the local host. With memory introspection, operators can detect malicious traces even with a compromised kernel. It usually relies on an outsider agent, commonly a hypervisor in online introspection, to snapshot raw memories from the guest virtual machine and conduct further forensics with the software libraries. Hypervisor-based introspection has been widely studied in the past. However, hypervisor-based introspection falls short in several aspects. It causes performance interference with the local workloads because both of them are co-located on the same machine. Meanwhile, such introspection system contains a huge trusted computing base, which induces vulnerabilities. Moreover, hypervisor-based introspection is not capable to support bare metal installations, which is emergently deployed in the cloud. We wonder how we can improve memory introspection in the cloud to achieve better security. We advocate for the concept of domain-1 security offloading. We draw our inspirations from the recent trend of hardware offloading. We wonder if we can solve the problem by moving one layer below from hypervisor to a lower level hardware, which we call domain-1. We would like to offload security tasks into widely deployed hardware in the infrastructure in the cloud, which operate beneath the hypervisors to enforce efficient security executions. With that, we will also be able to support bare metal installations for memory introspection. The opportunities for enabling domain-1 memory introspection come from the emerging networking hardware deployed in the cloud. The first technology which can be utilized is called remote direct memory access. RDMA enables reading and writing remote memory with CPU bypassed. RNIC can perform DMA to remote memory over network. RDMA has been widely deployed in clouds, and with RDMA, we can build efficient memory data path for domain-1 introspection. However, there is still one missing piece that we need an efficient controller for initializing RDMA read logic. We got solution from programmable switch. Programmable switch can be programmed with high-level languages like P4. The switch can be used to parse RDM headers and enforce match action tables as well as stateful operations. They run at line speed and are commercially available. Programmable switch has been widely used for networking security in the past, but this work is the first to use them for kernel security. We can utilize programmable switch to efficiently enforce control logic for introspection. To this end, we introduce RDMI, Remote Direct Memory Introspection, as a new paradigm for memory introspection. RDMI utilizes widely deployed hardware in the cloud infrastructure to enforce memory introspection. RDMI is formed of three components. First, we design a domain-specific language to serve as introspection abstractions, hiding low programming details, which is error-prone. We also design an intermediate representation called abstract introspection machine instruction set for better resource sharing and live deployment. Lastly, we designed the RDMI runtime, which consists of reconfigurable engines to instantiate AIM instructions and enforce memory introspections. There are several strengths of RDMI. RDMI is capable to support bare metal installation security. It also conducts remote execution with small local interference. RDMI runs fast and efficient introspections with the deployment of commercial off-the-shelf hardware. What's more, RDMI supports programmable policies with declarative domain-specific language. In short, RDMI offers protection with several new benefits. Here's the outline of the rest of the presentation. Moving forward, we will now introduce the detailed RDMI design. The first part we want to introduce is RDMI's domain-specific language for introspection. The insights of RDMI's DSL comes from the similarity between kernel memory introspection and graph processing. Take this figure as an example. Kernel data structures weave like a huge graph, where each object is the node in the graph and the pointers inside the node is the edges. To give a more concrete example, this MM pointer inside the task struct connects the task struct and MM struct node. By dereferencing the pointer, one can land on a different object and extract the information there. An example forensic query could ask to start from a well-known symbol, for example, this init task, and follow the next task pointer and loop the task struct linked list and get each running process ID. Inspired by this, we adapted Gremlin, which is a graph processing language, and built our own introspection primitives. Those primitives capture the common patterns in introspection logics. We will use an example query to introduce some of the primitives we developed. The query example we show here is to go through all the process described list and retrieve the process ID of each running process. The introspection first starts at a well-known symbol called init task with a concrete address in memory. It then calls traverse primitive to go through the linked list one by one by following the next pointer inside each task struct until it hits back the starting point. The next primitive we called here is a value primitive, which specifies the fields of interest we want to extract. This primitive is nested executed in traverse primitive, and it will return information while traversing each object. We constructed 11 queries, which are collected from previous memory introspection work. RDMI can express a range of useful introspection queries, and those queries can be expressed efficiently with only a few lines of code. Next, let us dive into the compilation process of DSL. A naive approach is to directly compile the DSL into P4 program and deploy it onto the switch. However, this will cause problems. In this way, changing and deploying new policies will incur downtime in order to flush the switch program. Thus, the queries cannot be deployed in a live manner, and taking down the switch will disrupt normal traffic. What's more, different policies might share the same execution patterns, which can be resource optimized and reused. Compiling directly will make it hard to capture such patterns across primitives and policies. We introduced abstract introspection machine as an intermediate representation layer inside RDMI. The AIM instruction set consists of 5 instructions, which capture the introspection patterns and are sufficient to express primitives. Those instructions serve as the underlying building block of the DSL queries. And for a deeper level, those instructions are implemented in a master switch program for execution. And this master program will be deployed only once. AIM serves as a bridge in RDMI. Here we show the whole workflow involving AIM. DSL will be compiled into AIM instructions, and they will be further compiled by the back-end compiler to configure the match action table inside the switch for encoding the introspection logic. We now introduce the reconfigurable engines in the master switch program that executes the AIM we just mentioned. A switch composes several runtime engines. For example, Indianness, an address translation engine, as well as the AIM engine. Those engines instantiate the AIM instructions, and match action tables building up those engines are reconfigured with different AIM instruction streams. That concludes the last design part of RDMI. Now let's move to the evaluation parts. Here's the setup of our experiment. Our baseline shown here is the libVMI-based introspection. We collected several real-world rootkits threads for evaluating the effectiveness of our system. We evaluated on some real-world applications like Redis and Nginx server to measure the workload degradation. We now present the result of our evaluations. The first evaluation we show here is the introspection effectiveness. We want to see whether our system can successfully capture the real-world threats. We deployed those rootkits into our servers and deployed the policies for detection. As we can see, RDMI effectively detects the real-world rootkits, and the deployment of RDMI didn't affect the normal traffics. The second experiment we show here is the throughput reduction of the Redis operations while running libVMI and RDMI introspections. We set libVMI and RDMI to run in the same frequency in this experiment for fair comparison. We see that RDMI causes negligible workload interference to the local applications. We have more evaluation results in our paper. Please refer there for more details. To summarize, we propose the domain -1 security offloading, which offloads memory introspection onto widely deployed hardware in the cloud infrastructure for better security. We introduce remote direct memory introspection and design its domain-specific language, abstract introspection machine, and runtime. RDMI improves cloud security on several aspects, such as bare metal installation support and higher attack detection rates. Our code has been open sourced via GitHub. With that, I would like to conclude my talk. Thanks for your attention, and I'm happy to take questions.